Welcome to Juttle in Action. Jut is an analytics platform for both live streaming and batch analytics for all different types of data. To allow users to work with their data, we've created a data flow programming language called Juttle. Juttle gives users one interface for all data controls, manipulation, and visualizations. We're going to walk through an example of putting Juttle to use in a real-world scenario. As we move through the steps, you'll see Juttle's many unique strengths. If you're new to Jut, you may want to first familiarize yourself with the components of a Jut deployment and language basics at the Juttle Playground. Our example environment is a file-sharing application. It has already been instrumented with collectd to gather host system metrics like memory and CPU utilization, statsd to gather application metrics like response time of our file serving, syslog to gather web server logs that reflect end-user downloads over HTTP, and HTTP callouts in our chef recipes that notify when we make config changes to the application. In our Jut deployment, these first two appear as metrics, while the latter two appear as events. The problem we're solving is poor response time to our file-serving clients. The application has traditionally been serving files off spinning disks, and we'll use Juttle to analyze data about the running environment to prove the value of using solid-state drives instead. We've already used Juttle to build our charts, so let's quickly walk through them and see how they show the effects of our config change, then we'll drill down into the code. Since we're interested in I/O performance, this first chart simply plots the percentage of time the host CPU is waiting on storage. We can now see that one of the two cores is consistently spending around 30% of its time waiting on the storage. This next chart plots our application response times. Here we're plotting the average time to first byte and time to last byte of file transfers to our end users. The third chart plots successful user download counts as gleaned from our web server logs. And our final chart plots the throughput across all user downloads whenever the server is actively sending to users, which is currently just below a gigabit per second. Now that the plots have shown us a baseline for performance for the spinning disk case, let's make our app change. We've staged the files in both the spinning and SSD-based mount points. We modify our chef recipe to point to the SSD mount point, then pull the trigger so chef processes the config change. Back in our Jut window, we can see the effects of the change reflected in our plots of our live data feed. An event sent by our chef recipe appears directly on our charts in line with the time series metric data. The metrics are showing us the kind of change we expected, with a significant drop in the amount of time the host is spending waiting on I/O. The time to first byte and time to last byte as reported by the app are also much lower, which makes sense since the server is no longer waiting on disk seeks. Our client download count has actually gone up slightly, indicating that the improved storage performance has helped us handle latent demand. And the aggregate throughput of our app when serving has rocketed from under a gigabit per second to around 3 gigabits per second. Just to make it crystal clear, let's back out our config change and go back to spinning disk. We once again see the event marker, and our metrics have gone back to where they were before. So how was it all done? It's all possible because of how Juttle works. Let's take a closer look at the programs that powered our charts. Here's the code for the chart of how much time the CPU spends waiting on I/O, which uses metrics that came from collectd. Like all of the charts we'll show here, we've set it up to always start by showing the last 5 minutes of historical data for this metric, after which it will continue displaying live points as they arrive. The first thing we see is that Juttle is a declarative language. In our code, we say what we want to have happen, which is pull the CPU wait metrics and plot them on a time chart, rather than how that's accomplished. This simple program also shows how expressive Juttle is. The way we specify the time range here will be easily understandable even to non-programmers, and is much easier to read and write than a lengthy timestamp. Here's the code for the chart of application response times, which were sent to us by statsd. Notice how we easily employed two axes to observe the correlation of metrics that are in order of magnitude apart. Now let's start looking at events. We've got syslog sending our web server logs to our Jut deployment, and it's very easy to get a quick look at them. However, there's too much detail to look at in a table, so let's use Juttle to crunch down the data to just that part that interests us. We know that successful client downloads will have an HTTP response code in the 200 range, so we'll use Juttle to isolate just those events. Then we'll batch them into 5-second groups, count how many are in each group, and then plot each of those counts. Now we have historical and ongoing live visibility as to how much user traffic is hitting our app. Let's add the application metric for our server throughput chart. For each client download, the app is keeping track of the number of bytes served and how much time it took to download, and StatsD is sending us totals for each of those every 10 seconds. Here's a look at the raw numbers. Let's say we want to turn that into a throughput value. We have one value for each metric each time StatsD reports. We can give each value a unique name, merge those two branches of our flow graph, and join on time to turn that into a single row of data. Here we see another benefit of Juddle. This Explorer environment makes for an interactive experience. The Explorer gives you constant feedback to let you know if your program is syntactically correct, so you spend less time debugging. And because we combine sources of data, analysis, and visualization all in a small amount of code, it's very easy to see the impact of small changes. Once joined, we'll add in some simple math to create the new throughput field. We'll turn the byte count into megabits and convert the serving time from milliseconds to seconds. Finally, we chart the calculated throughput value. Juddle also makes it easy to modularize your code for readability and reuse. Let's take our math that turned our metrics into megabits per second and break it into a function that can be imported. Like our other saved Juddle programs, this module is now available for import by others in our environment. You can also import directly from GitHub Gists if you want to share and leverage code with the wider Juddle community outside your organization. Finally, you may have noticed an extra line of code in each of our programs. Our chef recipes are instrumented such that they generate an HTTP event after each configuration change. By specifying the chart on which to place the annotations, Juddle will mark our time charts for us whenever a configuration change kicks in. Our initial set of 4 charts were generated by putting this code all in a single program. Here it is again with one final change. We've made it historical only, locking in the time range during which we made config changes. Now that we've got a concise set of charts that show the impact of our changes, we can use the share option of the Explorer to send a link for our charts to others. Of course, we were just working with a single host and a single application here to make it easy to explain in a quick video. Juddle makes it easy to correlate data from dozens of apps and thousands of hosts simultaneously, pulling in metrics and events data over long historical periods. To work with Juddle yourself, visit the Juddle Playground, where you can work with our data sources, edit sample programs to see the benefits of your changes immediately, and even write programs of your own to work with your data.